So in 1994, Professor Peter Shor out of MIT discovered what's now known as Shor's algorithm. And Shor's algorithm is a quantum algorithm, so it's an algorithm that runs on a quantum computer using qubits. And this algorithm provides an exponential speedup over classical computers for solving this exact problem, this integer factorization problem. Shor's algorithm can also be used to crack the discrete logarithm problem and the elliptic curve discrete logarithm problem. These other math problems are used for the elliptic curve variants of the asymmetric protocols we're talking about. So what does this mean? This means that, if we can run Shor's algorithm, we'll be able to deduce private keys from public keys. So again, this product of P and Q is advertised publicly, which is okay because the assumption of RSA is that it's okay, you can know N, but you're not going to be able to factor it into P and Q, so my private key is still secure. That's no longer the case with Shor's algorithm because we can really factor N much faster, exponentially faster than a classical computer. So this means that RSA, Diffie-Hellman, and their elliptic curve variants, all of these crypto systems that we rely on today will be completely broken by a sufficiently powerful quantum computer. There's another quantum algorithm that also is relevant to cybersecurity, and that's called Grover's algorithm. So Grover's algorithm is another quantum algorithm that provides a speed up for what's called brute force search. Now, it's not an exponential speed up, which is important. It's only a quadratic speed up, but it's still something we need to take into account. So let's take an example. If we want to crack a 128-bit key, we can do that much faster with Grover's. So the way it was done traditionally with a regular computer, okay, if we're searching for a 128-bit key, one that cracks some kind of a ciphertext, so one that successfully decrypts a ciphertext, we'll have to search over all 2 to the 128 possible keys. However, with Grover's, you can do that in around 2 to the 64 iterations instead. So it provides a speed up over classical computers. It's not exponential, but it's still notable. So Grover's algorithm does in fact endanger data that's encrypted and stored on online servers. Not only can it be used to speed up a brute force search for a symmetric key, but it can be also used to reverse engineer a cryptographic hash function. So these hash functions are used in our crypto systems. Let's say SHA-256, for example, is a standardized hashing algorithm. And Grover's can reduce the time to find the input of a hash output. So this has implications in collision attacks and birthday surprise attacks. Okay, so with Shor's and Grover's, what does this mean? Why is Q-Day so important to think about, and why is it a little daunting? That's because, once we have Shor's and Grover's, identity over the internet is no longer guaranteed. So your documents, messages, your web certificates, software you download, financial transactions, these can all be forged because of the implications of Shor's and Grover's. Your secret keys are exposed, so adversaries can read whatever you're receiving. Internet traffic is no longer secure. And this last point is one that's sometimes overlooked. People think, oh, this is something down the road I have to worry about down the road. No, this actually has implications right now. And the reason for that is what's called harvest now, decrypt later attacks. So what that means is, an adversary today can just be harvesting and collecting the encrypted data. They can't read it right now, but as soon as a sufficiently powerful quantum computer comes to play, then they'll be able to recover and decrypt all of that data. So the data you're sending right now, if you're using protocols like RSA or Diffie-Hellman, they can be harvested, that encrypted data, and then at a later date, when Q-Day comes, they can actually decrypt all of that. So any sensitive data that's being encrypted right now is also vulnerable to quantum attack at a later date.